Hello everyone, I'm Magnus Korpas from NTNU Norway, and I'm going to hold a presentation how costs are recovered in electricity markets with wind, solar and storage plants, an analytical approach. The presentation is largely based on material I've been working on together with Dr. Audun Botterud from MIT. The presentation builds upon our current working paper in the MIT CEPR series titled Optimality Conditions and Cost Recovery in Electricity Markets with Variable Renewable Energy and Energy Storage. We started this research by exploring how renewable energy and energy storage influence the profitability of different generation assets in the market. A common hypothesis is that traditional electricity markets fail under large-scale penetration of wind and solar, since they are driven by natural variations in the energy source and produce with zero marginal cost. This is foreseen to lead to price collapse, and plants needed for balancing are pushed out of the market, causing problems. However, our results using well-established power market theory as a starting point is that there exists market equilibria where all plants recovers their costs, and the prices are well defined over the course of the year. Therefore, our suggestion is to think twice before embarking on complete redesign of electricity markets. If we first look at the present markets, the merit order effect of wind and solar is already evident in many places. Several studies based on real market data conclude that prices decline with the integration of renewables. Notice, however, that other price effects can be much more dominant, such as the gas price effect observed in the US markets between 2018 and 2016. Many researchers have also analyzed how increased renewable penetration reduces prices using detailed power market simulations. The figure shows the estimated effect in several US studies, and similar results are found for Europe. Now, many market simulations assumes generation portfolios which are not in economic equilibrium, and they also often does not analyze the profitability of the variable renewable energy sources in particular. The main reason that the profitability of renewable plants have not been studied so much so far is that up to now, investments in these technologies and storage devices have been driven partly by incentive schemes and policies. But the cost reductions in these technologies has changed this picture in the recent years. It is therefore also a growing interest now by researchers, both in the engineering and economics fields, in how these technologies influence thermal generation investment and market equilibrium in competitive markets. To give an idea, though, about the renewable penetration levels we are talking about, I first want to highlight some recent results from another study that we have recently published with the main author Mehdi Jafari, also from MIT. The study is about power system decarbonization pathways for Italy by 2050. The work is based on power system optimization using cost scenarios for technologies and fuels for 2050. Looking at the figure to the left, it is evident that renewables takes a dominating role even without penalties for carbon emissions. I also want to emphasize that no renewables support is assumed here, only the expected cost reduction from the scenarios given by the European Commission in their reference scenario. Now, with the figure to the right, we have added storage in the system, and we see a remarkable positive effect on the optimal solar PV capacity. So there is a clear connection between the storage opportunity and the total amount of PV in the system. But these results are, as previously said, obtained by a system optimization approach, which takes the central planner's perspective, minimizing total costs of the system. But how will this work in a competitive power market? Will the short-term prices resulting from such generation mixes be sufficient to recover the long-term costs of all the installed assets? Our fundament is the basic energy-only market based on marginal cost pricing. Classical works, particularly from MIT, dated back to the 70s and 80s, show how such market design lead to system optimal investments and operation in equilibrium. In this equilibrium, all generator companies, which are price takers, will maximize their profits and recover their costs exactly. However, the classical work was limited to traditional thermal generation, and limited analysis has been carried out for renewable energy sources and storage systems. With a few good exceptions though, such as Stefan and Weber's excellent article in Energy Economics from 2013. In our model, it is scarcity pricing that ensures cost recovery of the peaker. And peaker is the most expensive generator in our system. We assume no payment for firm capacity or any subsidy for renewables or storage devices. The figure shows our simplified power system. We have simplified it as much as we can. No grid constraints. It's a copper plate model, so to say. The demand is fixed, except if a scarcity situation forces some of the load to be shed, then at a very high scarcity price. The baseload plant and peaker plant are thermal generators. The baseload has high capital cost and low marginal cost, while the peaker is cheap to install but expensive to operate. Variable renewable energy can be wind or solar and is characterized by high investment cost and zero marginal costs. Energy storage is represented by its charging and discharging losses, its power capacity, and its energy capacity. Now, if we take the central planner's approach, the problem is to find the plant capacities and operation which minimizes the cost of the delivered energy. The objective function is thus to minimize C for cost, which is the annualized investment cost plus the annual operation cost. The system shown in the figure gives rise to a set of mathematical constraints for this optimization problem. These are plant constraints, load balance constraint for every time step, energy storage constraints, availability limitations for variable renewable energy in every time step, and grid constraints are of course of very high importance in real system, but in the simplified model here, we have not taken these into account, just to keep modeling complexity as low as possible at this stage. Grid constraints can be added at a later stage of modeling. Now, moving from a system planner's problem to a market setting, we must address how the owners of the different plants interact with the market, both in the short and the long run. Each generator owner's objective is then to find their plant capacities and plant operation, which maximizes their individual profits. This can be formulated mathematically as to maximize pi, which is the annual market revenues subtracted the annual operating cost and the annualized investment costs. Now, An important assumption for our study is that we base the derivation on perfect markets. This implies that each plant owner is too small to influence the price individually, and that the generators bid their marginal cost, and the storage owner will then bid their marginal value of stored energy, often denoted as opportunity cost of storage. So, following traditional power market literature, we take a duration curve approach for analyzing the optimal investments and operation of the system. The approach is simply to sort the yearly time series of demand with the highest value first, as shown in the figure. In this example, the baseload plant is operating the whole year, while the total operating hours of the peaker is denoted TP in the picture. The duration of load shedding is TS, and this is the amount of hours where the installed capacity is not sufficient to cover all the demand. During those hours, we have a scarcity price, and the peaker plant can recover its cost during that period. So system optimality conditions for this system gives the exact expressions for the optimal duration of all the generators, the thermal generators in the system. And this is done by basically taking the derivative of the total cost with respect to each generator's capacity and set that to 0. While going for the market approach, we set up the profit maximization equation for all the generators, and also the profit maximization gives the exact same result for the thermal generator capacities and operation hours. And finally, all the costs have to be ensured to be recovered in optimum. So the profits over the year is 0. So these are well-known results from classic power market literature. So now we add the variable renewable energy, and let's say that it's wind power, just to be specific. So the figure shows a system with high amounts of wind power, where the shaded line is the original duration curve of the demand, while the black curve is the duration curve of the net demand, which is the demand seen by the thermal generators after subtracting the wind generation. In our case, we see that the net demand is negative for some hours of the year, which will be the result if the capital cost of wind power is low enough. In these hours, the thermal generation are 0, and wind power must be curtailed in order to meet the load balance. And the price is therefore 0, as it is the variable renewable energy that sets the price. So the optimality condition for the peaker and the baseload plant are not changed when wind enters the picture. This is due to the simple fact that all generators only earns money when the prices in the market is higher than their operating cost. Therefore, the durations of load shedding and peaker operation is constant and independent on wind installation. So in the figure, the duration of the baseload plant is denoted TB. Above this point, the net demand is negative and the price is therefore 0, as said. Therefore, the wind power plant only earns money up to this point. And the duration of the baseload plant is thus derived from the optimality condition of the wind farm and can be expressed analytically from the main optimization problem, which we showed earlier. And the analytical model shows that the market equilibrium with wind power will give less baseload capacity and energy delivered from that plant, and slightly more peaker capacity, and some more load shedding, and of course some wind curtailment, as earlier described. Now, finally, we let energy storage enter the market. Storage links energy content in time, and it's therefore not possible to include directly in a duration curve approach as we have used here. So we have to do some simplifications. We can model explicitly the power capacity and round trip efficiency, but not the kVH constraint of the storage. So we must relax the storage constraint in this in the model and use simplified operating assumptions for storage. And we have explored some variants of that in our paper, and we'll explain two of these briefly now. The first storage model we propose only allows storing surplus wind energy, but can shift the stored energy to any other time of the year. This is shown in the figure as the shaded areas. The area to the right is the stored surplus wind energy, and the area to the left is the discharged energy. And you can see that it replaces some load shedding and some energy from the peaker plant. So how does this storage operation influence the prices in the market? We find that the optimality condition for the storage determines the duration of maximum charging of the device. Now going from the left to the figure, in the figure, the prices are unchanged as long as the thermal generators are operating, since the storage is not the marginal generator in any of these segments. But in the segment between TB and TV in the figure, the price is set by the marginal value of storing the energy, since the storage is actually the marginal load here. And the marginal value of stored energy is basically what it can earn when the energy is discharged at a later stage. And in our case, that is to replace some baseload generation. So the price is then set by the baseload marginal cost, but adjusted for efficiency losses in the storage cycle. That means that the price is the efficiency multiplied by the variable cost of the baseload plant. Now beyond this point TV, the storage operates at full charging capacity, and some wind power must be curtailed as before. The price is therefore 0. So introduction of storage creates a new price segment where EES is storage is the marginal load, and this increases the optimal amount of renewables in the market, since we have a new price segment where the renewables can earn money. This is the most important result of that model. And the thermal capacity will be reduced even further due to the discharge of the stored energy during the high price periods. The second storage model is slightly more advanced. We now try to indirectly represent energy storage limitations by adding some restrictions to the operation. The surplus wind power is now assumed to only replace baseload power instead of the unlimited shifting capability that we used in the previous model. This limitation is set in order not to overestimate the capability of storing surplus renewable energy over very long times, which might not be feasible for storage devices such as batteries. But at the same time, we now also introduce the possibility to shift energy from the baseload period to the periods where load shedding and the peaker sets the price. Thus, the storage is a multi-purpose unit used for general price arbitrage in the market. So, as before, the storage sets the price when it's the marginal load, which is between TB and TV. And in addition now, the storage sets the price when it's the marginal generator, when discharges stored baseload power to replace peaking capacity or peaking generation. This is between the segments TP and TE in the figure. And therefore, the storage can be said to partly act as a mid-merit generator between the peaker and the baseload plant, and partly as an enabler for surplus wind energy. So if we write out the optimality conditions for the baseload plant, the storage, and the wind power plant, they will form a set of 4 nonlinear equations with 4 unknowns, which are the segments shown in the figure, TP, TE, TB, and TV. The reason why we get 4 equations is that we also have energy conservation, which must be guaranteed, which is just that the total amount of stored energy should be equal to, or must be equal to, the total amount of discharged energy over the course of the year. Now note that the optimality condition of the peaker is unchanged from before, as its cost recovery still comes from the load shedding period. And when the optimal durations of the different price segments are found, we can easily calculate the optimal plant capacities from the net demand duration curve. So by investigating this analytical model, we can come to some general conclusions without setting up any numerical examples, because the equations show the relations between the different plants and costs. So first, we show that profit maximization in a perfect market give exactly the same optimality conditions as system cost minimum, even with variable renewables and storage in the system. And all plants exactly recovers their costs in system optimum for all different types of plants. Further, by assuming linear scaling of renewable energy output, this is a simplification though, we find that the optimal renewable capacity is always will lead to some excess energy as long as it is profitable to install this type of plant. And this excess energy can be utilized by energy storage, which triggers even more renewable capacity in the market due to the new price segments created by the storage. And the secondary effect of this is reduced need for thermal capacity and a reduction in the market price over the course of the year. So to visualize some features of the analytical model, we have created a simple numerical example based on data and scenarios for the renewable power system, but without grid constraints. So costs and technology data is mainly based on the European Commission's 2050 scenario with some additional sources, such as a recent battery cost study from NREL. The modeled renewable energy source is chosen to be offshore wind, while storage is either pumped storage for long-term storage or lithium-ion batteries for short-term storage. So we set up 3 main cases: case 1 with only thermal, case 2 with wind in addition, and case 3 with storage in addition to that. So first, we show how the optimal generation capacities and market prices develops when wind and storage enter the system. Wind mainly replaces baseload plant, and without the storage device, it triggers some more peaking capacity due to the change in the net demand curve. Wind power alone leads to large amount of zero price hours, which is determined from the optimality condition of the wind power plant. And the average price is reduced a lot, as we can see. With the storage included, we get two new price segments according to the analytical model, and it triggers more wind power capacity, and the need for thermal capacity is further reduced. The optimal storage operation leads to flattening of the price variations in the market, but the reduction in average price is low compared to the isolated effect of wind power alone. More importantly, the results show that both wind power and storage leads to significant lower emissions, since a lot of the thermal generation of the air is now cut. With the analytical model, we can easily perform some sensitivity analysis on technology cost. Here we show how the wind energy penetration increases as a function of its capital cost. Notice that the x-axis is reversed, so there's a sharp increase in the beginning where wind power suddenly becomes profitable. After that, there is a clear saturation effect due to the quickly growing correlation between wind output and the prices in the market. We can also plot the wind energy penetration as a function of the resulting installed wind capacity, where we observe an expected saturation effect as more wind energy is curtailed. Now, continuing with the case with only thermal generators and wind power, we calculate the levelized cost of electricity for different plants and the average cost of electricity for the consumer. Again, the results are plotted as a function of wind capital cost with the reversed x-axis. So as wind costs are going down, the average cost of electricity is reduced. So this is the red curve. Thus, in this perspective, we can say that the system cost of competitive wind power in fact is negative, since the long-term customer price of electricity would be higher without it. And the LCOE of the baseload plant is shown in blue. This is increased since the number of hours of operation goes heavily down when wind enters the market. So the LCOE of wind is of course reduced as capital cost goes down. The purple graph is the LCOE that potentially could have been achieved for the wind power plant if there were no wind curtailments. And finally, we make a sensitivity analysis of the storage capital cost, also given on the reversed x-axis. The dotted line in both figures shows the capital cost where storage capacity is triggered. When capital costs are reduced below this level, the storage capacity increases and the operating hours of the baseload plant is reduced. This is shown in the upper figure as TB, the red line. And at the same time, the storage device creates a new price segment between the blue and the red curve, where the value of stored surplus energy sets the price. Now this new price segment makes wind power even more profitable than before and leads to more and more removal of thermal capacity from the system. So to wrap up, we can conclude with the following. All plants recover their costs in a perfect market with competitive renewable energy sources and energy storage. This gives the optimal generation mix, which minimizes system cost. And we get the same result when modeling the system containing of profit maximizing generator and storage firms. So our results therefore indicate that thermal generators, renewables, and storage can coexist in regular energy-only markets, but the capacity mix will of course change when these technologies enters the market. But this is in principle no different than when new cheap thermal generation enters similar markets. So finally, we have shown analytically exactly how storage devices will trigger more renewable capacity in the market. So the presence of storage creates a new price segment based on the marginal value of storage. And during this period, the renewable plants gain additional profits, and this result has itself several implications for the market equilibrium. So storage pushes more thermal capacity out of the market, both because of its balancing capacity and also because it triggers more renewable investments. And the storage leads to lower total amount of curtailed wind and solar in equilibrium, although it triggers more investments in these technologies. And we will say that the main benefit of storage is to increase the renewable share in the system and consequently further reduce emission caused by thermal generation. Our results have indicated that this emission benefit is much more evident from the results than the impacts on the average electricity cost alone. And that concludes my presentation. Thanks for listening, and here is the references.